In this video, we develop relations that can be used for the calculation of changes of internal energy, enthalpy, and entropy. Thermodynamic functions are not directly measurable quantities. Their value can be retrieved only from other measurable quantities. In order to compute the change of internal energy, enthalpy, or entropy, it is desirable to use two among temperature, pressure, or volume as independent variables, and also to express the various partial differential coefficients in terms of measurable quantities. This video develops a set of correlations which are based only on measurable quantities and that can be used for the actual calculation of changes in internal energy, enthalpy, and entropy. Two among these three thermodynamic functions are enough to calculate the changes of all other thermodynamic functions by means of their definitions. We start with the internal energy U. The objective is to find an expression for the change in the internal energy, which depends only on temperature and volume. The expression we want to obtain is the one in the red box. We will use again a well-known Maxwell relation. We have seen that the partial derivative of the pressure over temperature at constant volume is ultimately equivalent to the ratio between alpha, the coefficient of thermal expansion, and K, the isothermal compressibility. We use also the relation between heat capacity at constant volume and entropy. All passages we make run under the assumption of no change of composition, and that the change of internal energy happens through a reversible transformation. We start from the fundamental equation of thermodynamics for internal energy, in case of reversible transformation and no change of composition. We notice that the internal energy is here a function of entropy and volume, while we wish to have a relation in which only temperature and volume are present. Therefore, we develop the differential of entropy as a function of temperature and volume. The first entropy term is the heat capacity at constant volume. The second entropy term is ultimately the ratio between alpha, the coefficient of thermal expansion, and K, the isothermal compressibility. Developing further and moving to specific quantities, a finite change of specific internal energy is represented by the following expression, which is a function of temperature and volume. This expression can be used only if Cv and an equation of state, suitable for the specific fluid, are available. However, Cv and the equation of state are measurable entities in thermodynamics. Therefore, this relation represents the way to determine the internal energy from measurable quantities. Similarly can be done for the enthalpy. We wish to come to the expression in the red box, which represents a relation between the enthalpy change, the measurable quantity Cp, and a term depending on the equation of state. In this case, we are going to use the following Maxwell relation, combined with the definition of alpha, the coefficient of thermal expansion, together with the relation between Cp and entropy. We assume no change in composition, and that the change of enthalpy happens through a reversible transformation. Try to demonstrate the relation yourself. We start from the fundamental equation of thermodynamics for enthalpy, in case of no change of composition and reversible transformation. Enthalpy is here function of entropy and pressure. Therefore, we need to express entropy as a function of pressure and temperature. We use now the given equalities. Finally, we come to the SOP correlation. We can also express the correlation in specific and integral terms. Now we give two expressions for entropy. The first expression correlates entropy to volume and temperature. The second expression correlates entropy to pressure and temperature. We start with obtaining the expression in the red box, in which the change of entropy is a function of temperature and volume. We start with writing the expression for the change in the specific internal energy that we have just demonstrated. Then we write also the change in the internal energy as a function of entropy and volume, according to the fundamental equation of thermodynamics. In this second expression, we explicit the entropy change and substitute the internal energy with the expression above. This is done to obtain an expression which is only function of the specific volume and temperature. Now we develop the expression to obtain the one in the red box. We want now to express the change in entropy as a function of pressure and temperature. Our objective is to reach the final expression in the red box. We use the expression of the enthalpy that we have just developed in combination with the fundamental equation of thermodynamics for enthalpy. All subsequent passages are similar to the previous ones. We finally have an expression of the change in enthalpy as a function of Cp and quantities which can be retrieved from the equation of state. Let us briefly recap. When pressure and temperature are given, it's likely we are in an open system. In this case, having the Cp and the equation of state is enough to calculate enthalpy and entropy. All the other thermodynamic functions are then calculated in cascade from enthalpy and entropy by using the definition of the specific thermodynamic function or the fundamental equations of thermodynamics. When volume and temperature are given, it's likely we are in a closed system. In this case, having the Cv and the equation of state is enough to calculate internal energy and entropy. Also in this case, all the other thermodynamic functions are then calculated in cascade from internal energy and entropy by using the definition of the specific thermodynamic function or the fundamental equations of thermodynamics.